Morning, students. Last class we discussed about the morning, students. Last class we discussed about the numerical problems on oscillators. That means how to determine the voltage across each unit. That is nothing but each disk. Also total voltage across that string. Also string efficiency. So we have to calculate it in different manner, different situations. Sometimes they're given K value, then you have to determine V1, V2, V3, and then string efficiency. Sometimes they will given V1, V2. From that V1, V2, you have to determine K and then V3, then string efficiency. Sometimes they given K value and V3 value. For that, by using K and V3, we have to determine V1 and V2 and then string efficiency. So these are the individual problems. Suppose we have to improve the efficiency, we are utilizing Gaudring method. That is also discussed in the last class. Now we go for the numerical problems on corona and sag. So first of all, we discuss about the corona problems and then go for the sag problems. First of all, let us so the first problem: a three-phase line has conductor. A three-phase line has a conductors of 2 cm in diameter, spaced equilaterally 1 meter apart. If the dielectric strength of air is 30 kV maximum per centimeter, suppose it is given, it is not given also, you have to take in 30 kV per centimeter for maximum value. Suppose we are going to the RMS value 21.2 kV per centimeter is RMS values. They given, well and good. Suppose they don't given, so we can taken by these two values. Those are the standard values. 30 kV per centimeter maximum value, 21.2 per centimeter kV per centimeter is RMS value. And now find the descriptive critical voltage or critical descriptive voltage for the line. Take the air density factor delta 0.952 and irregularity factor M0 is 0.9. Suppose they don't given, you have to take in these values also, air density factor and irregularity factor. Smooth conductor or ACSR standard conductor, like that, you have different values. Now, what are the given data? Conductor radius R is equal to, so they given diameter 2 cm. That means radius is d by 2, that is 2 by 2. So 1 centimeter. Diameter is 2 cm. Therefore, conductor radius R is equal to d by 2, that is equal to 2 by 2 is 1 centimeter. Now conductor spacing, that is nothing but distance. Spaced equilaterally 1 meter apart, that is nothing but 1 meter. You have to put all in centimeters, otherwise you have to put all in meters. But so maximum the dielectric strength is in centimeters, that's why put all in centimeters. So D is equal to 1 meter, that is equal to 100 centimeter. Dielectric strength of air G0 is 30 kV per centimeter, they given directly, and we have to take in the RMS values 21.2 kV RMS for maximum value, right? And we know the empirical formula for critical descriptive voltage. What is the critical descriptive voltage? It is the minimum phase to neutral voltage at which corona occurs. That is nothing but ఎక్కడైతే కరోనా అక్కర్ అవుతుందో అక్కడ మాత్రమే వచ్చే వోల్టేజ్నే మనం క్రిటికల్ డిస్క్రిప్టివ్ వోల్టేజ్. దట్ ఈస్ ఎంపరికల్ ఫార్ములా ఫర్ క్రిటికల్ డిస్క్రిప్టివ్ వోల్టేజ్ M0 G0 delta R log D by R kV for phase RMS values. M0 they given 0.9 and G0 they given 30 kV for maximum value, but we have taken RMS values, that is 21.2, and delta they given 0.952 and R, that is 1 centimeter into 1 log D by R, spacing 100 centimeter, R 1 centimeter. Therefore, log 100 by 1 base E. By calculating all these things with a calculator, so we are getting critical descriptive voltage is 83.64 kV per phase. 83.64 kV per phase. That means, so 83.64 kilovolts The corona will be occurred on the line conductors. Suppose you are going to the line voltage. So critical descriptive voltage is nothing but phase voltage. It is a phase to neutral voltage. I mean minimum phase to neutral voltage. That is nothing but phase voltage. We are getting the line voltage multiplied with √3. So line voltage RMS is equal to √3 into phase voltage, that is 83.64. We are getting the 144.8 kV, right? So like this we have to calculating the critical descriptive voltage, and also sometimes they are asking visual critical voltage also, right? What is meant by visual critical voltage? This is also minimum phase to neutral voltage at which corona may view by the observer. That is nothing but observer may visual appearance by the observer. So go to the second problem. A 132 kV line with 1.956 centimeter dia conductors is built so that corona takes place. The line voltage exceeds 210 kV RMS. If the value of potential gradient at which ionization occurs can be taken as 30 kV per centimeter, find the spacing between the conductors. So we have to determine small d spacing between the conductors. So what are the, once again please observe the problem. They given line voltage, they given diameter, and they given corona may occurred this much of voltage, that is nothing but critical descriptive voltage. Where corona occurs and at which voltage corona occurs, critical descriptive voltage. So that is nothing but the given critical descriptive voltage, right? So assuming the line is three phase, right? Conductor R is equal to the given diameter 1.956 centimeter. Therefore, R is equal to D by 2, that is 1.956 by 2, that is 0.978 centimeter, right? Next, dielectric strength of air G0. So that is they given again 30 kV per centimeter, right? Maximum value, but we want RMS value. RMS value is nothing but maximum value by √2. So those are the standard values. 30 kV per centimeter for maximum value, and 21.2 kV per centimeter is the RMS value. So we don't need calculate, but suppose you have to calculate. So RMS value is equal to maximum value by √2. Therefore, 30 by √2 is equal to 21.2 kV per centimeter is the RMS value. And critical descriptive voltage, they given three phase. In problem three phase, but critical descriptive voltage normally phase voltage. That's why by √3, 210 kV they given. That is the line voltage. But we want phase voltage. That's why VC is equal to 210 by √3. That is equal to 121.25 kV. Now they don't given irregularity factor, right? That's why we have to assume whatever it may be. Suppose you have to take in smooth conductor, it is a 1. Otherwise, you have taken standard conductor, this is 0.92295, whatever it may be. But for our simplification of calculation, we go for the smooth conductor. They don't given, you have to take in any one. So that's why let us assume a smooth conductor. So for smooth conductor, irregularity factor is 1, that is M0 is equal to 1. In similar manner, air density factor is 1. You have to assume for standard pressure and standard temperature. Delta is also 1, right? Let us consider small d is the spacing between the conductors. Now, what is the formula for critical descriptive voltage in RMS? That is VC is equal to M0 G0 delta R log D by R base E kV kilovolts. We know the we have already assumed the irregularity factor M0 1 and G0 21.2 and delta 1, then R 0.978 into log D by R 0.978. So 121.25, that is the VC critical descriptive voltage, is equal to calculating all these things, multiplying all these things. 20.733 into log D by R is nothing but 0.978. So therefore log D by R is equal to 121.25 by 20.733, that is equal to 5.848. And then so log D by R, that is the base E. For our simplification, go to the base 10. So from base E to convert log base E to base 10 multiplication with 2.3. 2.3 log 10 d by r is equal to 5.848. Therefore log 10 d by r log d by r base 10 is equal to 5.848 by 2.3, that is equal to 2.5426. Now d by r is equal to 10 power 2.5426, otherwise anti-lag of 2.5426, that is equal to d by r is equal to 348.8. Now d is equal to 348.8 multiplied by r is nothing but 0.978, right? By multiplying those two, that is 348.8 into 0.978, that is equal to 341 centimeters, right? So this is the spacing between the conductors. So 341 centimeters, right? Like that, you have to calculate the spacing between the conductors from the critical descriptive voltage. Now go for the example 3, right? A 3-phase 220 kV 50 Hz transmission line consists of 1.5 centimeter radius conductor spaced 2 meters apart in equilateral triangular formation. If the temperature is 40 degrees centigrade and the atmospheric pressure is 76 centimeter, calculate the corona loss per kilometer of the line. Take m0 is equal to 0.85. In this problem, this is also 3-phase 220 kV line, 50 Hz transmission, 50 Hz frequency, and consists of 1.5 centimeter radius. They given directly radius r is equal to 1.5 centimeter, and then spacing is also given 2 meters, that is nothing but 200 centimeters. If the temperature is 40 degrees centigrade, pressure is 76 cm per Hg. Calculate the corona loss per kilometer. You have to calculate the corona loss. Taken m0 is equal to 0.85. Now what is the corona loss formula? P is equal to 242.2 into F plus 25 by delta root R by D into V minus Vc square into 10 power minus 5 kilowatt per kilometer per phase. Here V is nothing but V phase. So generally we have to write in V phase. That's why we have to take in as clarity. Why? Because Vc is also phase. That's why V is also phase. Now we have not taken line value. So, but we don't know delta value. First of all, you have to calculate the delta, air density factor. Delta is equal to 3.92 B divided by 273 plus T. B is nothing but barometric pressure. So 3.92 multiplied by 76 centimeter is the pressure. So into 76 divided by 273 plus temperature is 40 degrees. So 3.92 into 76 by 273 plus 40 is equal to 0.952 is the delta value. And let us assume G0 as usual. We have to take an RMS value, that is 21.2 kV per centimeter, right? So now we don't know critical descriptive voltage. First, let us calculate the critical descriptive voltage per phase. Vc is equal to, we know the formula, m0 g0 delta r log d by r base E kilovolts. So m0 0.85 they given, delta naught already we have to assume, that is 21.2 multiplied by delta 0.952, I have to calculate it, and then r is equal to 1.5 directly they given, and log spacing also they given 200 centimeters or 2 meters by 1.5. Then Vc is equal to 125.9 kV. By calculating the calculator, we are getting the critical descriptive voltage per phase is 125.9 kV, right? And they given supply voltage, that is 220 kV 3-phase per phase. So V phase is equal to 220 by root 3, that is 127 kV. And we know all the values included in the corona loss formula. That's why substitute all the values in the corona loss formula, we are getting the corona loss. P is equal to 242.2 into F 50 Hz plus 25 divided by delta 0.952 into root R by D. R is equal to 1.5 by D 200 multiplied by V minus Vc, that is V phase minus Vc. V phase is 127 minus Vc is 125.9 whole square into 10 power minus 5 kilowatt per phase per kilometer. And by calculating with calculator, we are getting 0.01999 kilowatt per kilometer per phase. That is the corona loss. Suppose in the problem they given three phase. That's why I have to calculate three phase. That is line corona loss per kilometer for three phase, not phase. Total corona loss per kilometer per phase is nothing but 0.01999 kilowatt per kilometer per phase. But you have to calculate three phase. So that's why multiplied with 3 into 0.01199 kilowatt is equal to 0.05998 kilowatt, right? So like this, we have to calculate the corona loss. First, we have to calculate the corona loss. First, we have to calculate the delta air density factor with the help of formula 3.92 into B divided by 273 plus T. And then G0 we have to assume standard value. And then we have to calculate the critical descriptive voltage. And then calculating the V, supply voltage per phase. Then substitute all the values, we are getting the corona loss. So also another problem. This is also what is the critical descriptive critical voltage and what is the corona loss at 113 kV. That is nothing but supply voltage is 113 kV and some confusion is there. So that is nothing but they given corona loss 53 kilowatt and they given second case corona loss 98 kilowatt at 110.9 kV phase voltage, line voltage. First case 53 kilowatt at 106 kV. In second case, they given corona loss at 98 kilowatt at 110.9 kV. Now, what is the critical descriptive voltage and what is the corona loss at 113 kV? They given two cases. Corona loss at supply voltage is 106 kV. Corona loss supply voltage is 110.9 kV. Now, what is the corona loss at 113 kV supply? And also calculate the critical descriptive voltage. We know the formula corona loss for three phase is directly we are putting three phase, right? Generally single phase 242.2 into F plus 25 by delta root R by D V minus VC square into 10 power minus 5 kilowatt per kilometer per phase, but into three phase into 3 multiplied by into 3. Right? So we know the P is proportional to V minus VC square. Therefore, so 53 proportional to 61.2 VC square, 98 proportional to 64 minus VC square by equation 1 and 2. Dividing equation 2 by 1, that is 98 by 53, 64 minus VC square by 61.2 minus VC square. We are solving the VC is equal to so 54 kV, right? If W is the kilowatt be the power loss and 113 kV. Suppose we have to assume W is the corona loss at 113 kV. Generally we are designated P, but we have to assume W because before we have to taken P. So W is equal to 113 by root 3 minus VC square. Why? Because supply voltage V is equal to 113 kV line voltage. That's why by root 3. So that is W proportional to 65.2 minus 54 square taken as equation 3. Now 3 by 1. Divide the equation 3 by 1. W by 53 equal to 65.2 minus 54 square by 61.2 minus 54 square. We are getting corona loss at 113 kV is 128 kilowatts, right? So next problem. This is till now we discuss about the corona loss problems. Now we discuss about the sag problems. A 132 kV transmission line has the following data. Weight of the conductor is 680 kg per kilometer. Length of the span 260 meters. Ultimate strength 3100 kg. Safety factor 2. Calculate the height above the ground at which the conductor should be supported. Ground clearance required is 10 meters. So weight of the conductor per meter W is equal to they given for kilometer. weight of the conductor for kilometer, but we want per meter, that is nothing but by 1000 divided by 1000. So 680 by 1000, that is equal to 0.68 kg. Now working tension T is equal to ultimate strength by safety factor. Generally safety factor is the ratio of ultimate strength by working tension. From that formula, ultimate tension, working tension is equal to ultimate strength by safety factor, that is 3100 by 2, that is 1550 kg, 1550 kg. Span length they given 260 meters. Now we know the formula for sag, omega L square by 80, W L square by 80. W is the weight of the conductor, that is 0.68 multiplied by L, 260 meters square divided by 8 into tension, that is 1550. We are getting sag is equal to 3.7 meters. But they don't asking sag. What is the height above the ground at which conductor should be supported? That is nothing but unequal space. Suppose equal space, that is nothing but sag. Unequal space, height is nothing but above the sag. So that's why conductor should be supported at a height of 10 plus 3.7. That is, so required ground clearance is 10 meters, and then sag, that is nothing but 10 plus 3.7, that is equal to 13.7 meters. Suppose they don't asking height of the conductor, so they asking sag just 3.7 meters. Suppose they asking height of the conductor, we can add the ground clearance distance with sag, that is 10 plus 3.7, that is 13.7 meters. Now go for the second problem. A transmission line has a span of 150 meters between the level supporters. So they given level supporters. Conductor has a cross section area of 2 centimeters square, and the tension is 2000 kg, and the specific gravity of the conductor material is 9.9 gram per centimeter cube. Wind pressure is 1.5 kg per meter length. Now calculate the sag and what is the vertical sag. After calculating the sag, you have to calculating the theta angle, and then S into cos theta is nothing but vertical sag. So look at the solution. The given data is span length is L is equal to 150 meters, working tension T is equal to 2000 kg, wind force per meter length of the conductor WW is 1.5 kg, weight of the conductor per meter length, that is equal to specific gravity multiplied by volume of the conductor, that is 9.9 into 2 into 100, that is 1980 gram or 1.98 kg. Now total weight is nothing but weight of the wood and also weight of the conductor. Vectorical representation of the weight of the conductor and also weight of the wind force of the conductor. So W square root of W plus WW square, that is the total weight of the conductor per meter length, that is square root of 1.98 square plus 1.5 square, that is equal to 2.48 kg. Now we have to calculate the sag. Sag is equal to omega T L square by 80, omega T total weight of the conductor. So 2.48 into 150 square divided by 8 into 2000. We are getting the sag is equal to 3.48 meters. Right? Look at the phasor diagram. From this phasor diagram, this is the wind force. Weight of the conductor because of wind force. This is the weight of the conductor. Weight of the conductor is always applied in vertically, and wind pressure always applicable in horizontally. Vectorical sum is nothing but total weight. Now observe this phasor diagram. Tan theta is equal to opposite by adjacent. Opposite is nothing but, what is the opposite? WW divided by adjacent is nothing but W. So WW by W, that is 1.5 by 1.98, right? That is equal to 0.76. Therefore theta is equal to tan inverse of 0.76, that is equal to 37.23 degrees. Now we go for the vertical sag, S cos theta. S is nothing but sag, 3.48 multiplied by cos 37.23 is equal to 2.77 meters. Now go for the another problem. So a transmission line has a span of 200 meters between level supporters. The conductor has a cross-sectional area of 1.29 centimeters square. Weight is 1170 kg per kilometer, and breaking stress is 4218 kg per centimeter square. Calculate the sag for a factor of safety is 5, allowing a wind pressure 122 kg per centimeter square of a projected area. What is the vertical sag? As usual, so this problem is also similar to that of previous problem. From the safety factor formula, safety factor is equal to ultimate strength or ultimate stress divided by working tension. So working tension or working test T is equal to, so ultimate stress or ultimate strength divided by safety factor. The given ultimate strength is 4218 divided by 5, that is equal to 843.6 kg per centimeter square. Tension is equal to, working stress is equal to 843.6 kg per centimeter square. But what about working tension? So it is having a multiplied with 1.29, that is nothing but the given cross sectional area. Suppose they don't given cross sectional area, we directly go for the, they directly given the working, directly find out the working tension, but they given clearly cross sectional area, stress multiplied by, so working stress multiplied by cross sectional area, that is equal to, so 843.6 multiplied by 1.29 is equal to 1.088 kg per weight. So W is equal to, they given for kilometer, right? 1170 kg per kilometer, but we don't want kilometer, we want meter, that's why by 1000, so that is equal to 1.17 kg weight per meter. Now let us now find diameter of the conductor from the equation. First of all, we have to calculate the diameter. So looking pi d square by 4, that is equal to 1.29. Cross section area A is equal to pi d square by 4, that is equal to 1.29. From that equation, we have to determine D is equal to 1.28 centimeter. D is equal to 1.28 centimeter. This is important problem. They are asking in previous paper also. First, we have to find out the safety working stress from the safety factor. From that working stress, multiply with cross section area, we are getting the tension, and then weight, the given kilometer, we are getting meter, that is nothing but divided by 1000, we are getting weight of the conductor, and then D, spacing. So diameter, not spacing, the diameter of the conductor is nothing but the given cross section area, that is pi by 4 d square, that is equal to 1.28 in the given problem. So from that we are determine the diameter 1.28 centimeter. Now projected area of the conductor for meter length is 1.28 into 10 power minus 2 in multiplied by 1, that is equal to, convert the centimeter into meters, that is equal to 1.28 into 10 power minus 2 meter square. Now total weight is a vector sum of weight of the conductor square plus weight due to the wind square, that is Wt is equal to square root of W square plus WW square. We know the W, that is weight of the conductor 1.17, but we don't know WW. So WW is equal to, they given clearly wind pressure 122 kg per meter square, that is nothing but per meter square, what is the area? 1.28 multiplied with plus 1. So weight of the wind is equal to 122 kg multiplied by 1.28 in 10 power minus 2, that is 1.56 kg per meter. Now we know the weight of the conductor, we know the weight due to wind pressure, then add vectorically, then we are getting total weight is equal to square root of W square plus WW square, that is equal to 1.17 square plus 1.56 square, that is equal to 1.95 kg per meter. And sag is equal to omega L square by 2t, omega L square by 2t. So why? Because omega L square by 2t, it is a unequal length, that's why we go for the omega L square by omega total L square by 2t. Suppose the given equator spacing L is equal to L by 2, that's why it is getting omega L square by 8t, right? So omega L square by 2t is equal to 1.95 into 100 square by 2 into 1088, that is 8.96 meter. From that we know the tan theta, before, as like before problem, tan theta is equal to WW by W. From that we are getting tan theta is equal to 1.333. From that theta is equal to tan inverse of 1.333 is equal to 53.2 degrees. Now calculate the vertical sag. Vertical sag is equal to S into cos theta, right? So here they mentioned D, not D, S, taken as S. S into cos theta, S into cos of 53.2, that is equal to 8.96 into 0.599, that is equal to 5.3 meters, right? So like this, we have to calculate the tension, we have to calculate the projected area, and then we will calculate the weight of the conductor due to wind pressure, and then calculate the total weight, then calculate the sag, and then vertical sag, right? So second problem and third problem is very, very important. Go for this problem is also similar as first problem. Calculating the conductor should be supported at a height of, that is nothing but S plus the given height. So an overhead line has a span of 150 meters between the level supporters. Conductor has a cross-section area of 2 centimeters square. The ultimate strength is 5000 kg per centimeter square, and the safety factor is 5. The specific gravity of the material is 8.9 gram per cubic centimeter. The wind pressure is 1.5 kg per meter. Calculate the height of the conductor above the ground level at which it should be supported with a minimum clearance of 7 meters. Right? Minimum clearance of 7 meters, they given. So now conductor should be supported at a height of is nothing but 7 plus sag. First of all, we have to calculate the sag, and then adding sag with 7 meters, we are getting the height of the conductor, right? Span length L is equal to 150 meters. Wind force WW 1.5 kg. Now weight of the conductor, they given for they don't given conductor. So conductor weight of the conductor is equal to conductor area multiplied by 100 centimeters multiplied by specific gravity. Then conductor area multiplied by specific gravity, but the given conductor area is 2 centimeters square. That is the cross sectional area. 2 into that may be 100 multiplied by 8.9, 100 centimeters into multiplied by specific gravity 8.9. We are getting 1780 gram. That may be converted into kg, that is by 1000, 1.78 kg. Now working tension T is equal to the given ultimate strength, right? And the given safety factor 5. So ultimate strength by safety factor is nothing but, so tension, working tension is equal to, so ultimate strength multiplied by 2 into divided by safety factor 5000 into 2 by 5, that is equal to 2000 kg. 2000 kg. Next, total weight, vectorical sum of WW plus W, that is square root of W square plus WW square, that is equal to square root of 1.78 square plus 1.5 square, that is 2.33 kg. Go for the formula, slant sag equal to omega T L square by 8T. We are getting 3.28 meters. Vertical sag is equal to S cos theta, 3.28 W by WT, W by WT, that is the tan theta. So for cos theta, WW by tan theta is equal to WW by W. But what about cos theta? W by W total, right? Adjacent by hypotenuse. So that's why you are getting directly 3.28 into 1.78 by 2.33, that is equal to 2.5 meters is the vertical sag. Now conductor height 7 meters plus sag, that is 7 meters plus vertical sag. We are getting vertical sag 2.5, that is equal to 9.5 meters. Similarly, we go for the another problem. A transmission line has a span of 150 meters between supporters. The supports being at the same level. Conductor has a cross-section area of 2 centimeters square. Again, ultimate strength is 5000 kg per centimeter square. The specific gravity of the material is 8.9. The wind pressure is 1.5 kg per meter length. Calculate the sag at the center of the conductor. Factor of safety is 5. As usual, definition of factor of safety. So this is also similar to the above problem. Factor of safety is equal to ultimate stress by working stress, or ultimate strength by working stress. So 5000 by 5, that is nothing but working stress is equal to ultimate stress by safety factor. Ultimate stress is 5000 kg, divided by safety factor is 5, that is equal to 10 cube kg per centimeter square. Now calculate the working tension. Working tension is nothing but 10 cube multiplied by with 2, that is nothing but cross section area. So working stress multiplied by cross section area is nothing but working tension, that is equal to 10 cube into 2, that is equal to 2000 kg per centimeter. Now weight for 1 meter, 8.9 into 200 gram, that is equal to 8.9 into 2000. 200 by convert into gram into kg. 200 by 1000, that is equal to 1.98 kg weight. Now we know the weight of the conductor and we know the weight due to the wind pressure. Now take a vectorical sum of both those two. We are getting total weight. W is equal to square root of W square plus WW square, that is 1.98 square plus 1.5 square root. We are getting total weight 2.48 kg. So therefore calculating the sag. Sag is nothing but omega L square by 2. There is nothing but, we don't calculate the slant sag or equal support sag. We have to calculate the sag at the center of the conductor. That is equal to omega L square by 2T only. So 2.48 into, so L is 150 meters. So there is nothing but, suppose you have taken L by 2, that is omega L square by 80. So 2.48 into 150 by 2 square in by 2 into 2000, we are getting 3.5 meters is the sag. Like this, you have to calculate the sag and total weight of the conductor and also working stress of the conductor. So go for the another problem. An overhead transmission line at river crossing supported from 2 towers with a height of 50 meters and 100 meters above the water level. The horizontal distance between the towers being 400 meters. If the maximum allowable tension is 1800 kg and the conductor weight is 1 kg per meter, find the clearance between the conductor and water at a point midway between the towers. That is nothing but they given unequal supporters and what is the clearance between the conductor and ground. So how much clearance is taken by the conductor to ground, we have to calculate. That is spacing D. Here H is equal to, they given difference between the heights 100 meters and 50 meters, that is H is equal to 100 minus 50 is equal to 50 meters. The L is equal to 400 meters, that is L is equal to L by 2, 400 by 2 is equal to 200 meters. They given tension 800 kg for weight and W is 1 kg for weight per meter. And this is a unequal supporters, that's why we have to calculate at a particular point from that x1 length and x2 length. x1 is equal to L minus ht by 2 omega L, x2 is equal to L plus ht by 2 omega L. By calculating x1 and x2, we are getting minus 25 meters 1 and 425 meters. So by substituting these x1 and x2 values, and we are getting the exact clearance between the ground to conductor, in the clearance distance between the conductor and ground. So this is the D midpoint, and D mid is equal to omega x square by t, and omega is 1 and 225 square by 2 into 1800, that is equal to 1400 meters. D2 omega x2 square by 2t. Suppose D1 omega x1 square by 2t. Like that we have to calculate it. D midpoint and also D D2 D1 also. So hence P is the 52.2 minus 14, that is 36.2 meter below the point B. Look at the figure. So you have taken the P is the point. From that, so midpoint P is 100 minus 36.2, that is equal to 63.8 meter above the water level. So we have to calculate the x1, we have to calculate the x2, and then calculate the x, then calculate d1, d2, d. From that, so P is nothing but d2 minus d midpoint, that is 36.2 meters. Now total is 100 minus so 36.2, we are getting the 63.8 meters from the water level. Similarly, another problem. This is also same problem, 30 meters and 90 meters. X1 is equal to L minus HT by 2 omega L, and X is equal to 250 minus 60 into, that is why, because 90 minus 30, that is the 60 H. Tension is equal to 1600 kg. W is equal to 1.5 kg per meter. Therefore, X is equal to L minus 250 minus 60 into 1600 by 2 into 1.5 into 250. 250 minus 128, that is 122 meters. X is equal to 122 meters. Therefore, X1 is equal to 250 plus 128, that is 378 meters. Now calculate the D1, omega x1 square by 2t, 1.5 into 122 square divided by 2 into 1600, that is 7 meters. Now unequal strength, P is the point, right? Now x2 is 378 meters, x1 is 122 meters, and P point is 250 meters. So height is 60 meters. So 30 minus 7, that is 23 meters. Now total 250 minus 122, that is 128. The height of that point P above O is 7.68. So now we have to distance at midpoint here. Only midpoint, they are asking midpoint 7.68 meters. But before problem, they are asking what is the height of the above. That's why 100 minus the 32 point, we are getting 63.8 meters. But here midpoint is equal to Wx1 square by 2t, right? Like this, you have to calculate the problems for SAG also. Look at the figure. First, we have to calculate the first height. H is equal to 90 minus 30, that is 60 meters. Tension they given 1600 kg per weight. W 1.5 kg per meter. Now X is equal to X2 is equal to 250 minus omega HT by omega L. X1 is equal to 250 plus 128, that is HT by 2 omega L. By calculating those two, we are getting this. Look at the figure. We have to take an assumption as P is the point. From that X1 value, from that X2 value, from that X value, right? So X is equal to 250 minus 122, right? So this is the total 250 meters. Now X1 is the 122. Now we have to calculate the X, means 250 minus 122, that is equal to X is equal to 250 minus 120, that is 128 meters. Now we have to calculate the height P point with the X value, that is equal to omega 1.5 into X1 square, that is X square, not X1 square, 128 square divided by 2 into 1600, that is the tension. So D midpoint is 3.68 meters, right? So like this, we have to calculate the SAG and the distance at equal levels and unequal levels, right? Thank you one and all. From this class, the third unit, that is third unit of a electrical power transmission system, is completed. That is mechanical design of overhead transmission line is complete. It contains 3 parts: insulators, corona, SAG. So insulators theory is completed, problem is completed, and corona theory is completed, problem completed, and also SAG theory completed, now problems also completed. So totally third unit is completed, right? Thank you one and all.